So, this is as far as magnitude response goes. Then we will move on to the other part of frequency response, namely phase response. So, we have h of e to the j omega. So, this is b naught times k going from 1 to cap n 1 minus z k e to the minus j omega by k going from 1 to cap n 1 minus p k e to the minus j omega. So, this is the form of the frequency response for rational transfer function, where we have factored the numerator and the denominator, and now we are looking at the angle, and the notation ARG is used to denote the angle of a complex number, ARG being the short form for argument, and you have k going from 1 to cap m arg of 1 minus zk e to the minus j omega minus k going from 1 to cap n arg of 1 minus pk e to the minus j omega. So, this pretty straightforward based on the formula for angle of ratio of complex numbers. So, now let us concentrate on one typical factor and get a feel for what is happening here. Therefore, we look at argument of 1 minus, let us take the 0 to be at r e to the j theta e to the minus j omega, and this of course is arg of 1 minus r cos omega minus theta plus j times r sin omega minus theta. All I have done is I have just multiplied this out and replaced e to the j by cos plus j sin, and this is nothing but tan inverse or sin omega minus theta by 1 minus r cos omega minus theta, and this tan inverse is the 4 quadrant inverse tan, and the reason why I am mentioning that is tan inverse 3 by 4 is not the same as tan inverse minus 3 by minus 4. So, we are looking at the 4 quadrant inverse tan here, and as theta changes, remember theta is the angle of the root, as theta changes, all that is going to happen to the phase response is shift the phase response either to the left or to the right. So, basically this is the phase response of a single complex 0. For illustrative purposes, let theta equal to 0. Similar to the geometric interpretation of the magnitude of a minus b, where a and b are complex numbers, that interpretation is it is the length of the vector joining these 2 points. Similarly, the geometric interpretation of the angle of the vector joining the 2 complex numbers is, if you have angle of a minus b, it is basically the angle of the vector joining these 2 points. So, we will exploit that interpretation and get a feel for the phase response, similar to getting a feel for the magnitude response geometrically. Therefore, if you have h of z is 1 minus r e to the j theta z inverse, this is the single complex 0. So, this is nothing but z minus r e to the j theta by z, and hence h of e to the j omega is e to the j omega minus r e to the j theta by e to the j omega, and then we are looking at angle of this, and this in turn is the angle of e to the j omega minus r e to the j theta minus angle of e to the j omega. So, this is and this is nothing but omega, because angle of e to the j omega is just omega. So, the reason why I am writing it like this is, remember this z, which is a trivial pole, didn't contribute to the magnitude response, but sure enough it can't be sitting in the expression and not contribute to both phase and magnitude. It didn't contribute to the magnitude, it is surely contributing to the phase as can be expected. So, 1 minus r e to the j theta z inverse, which is z minus r e to the j theta by z. So, you have a trivial pole, and for illustrative purposes I am going to use theta equal to 0. Therefore, I have a 0 sitting here. And this is a general point on the unit circle, and now I am going to draw upon the geometric interpretation to get a feel for what is going on. So, let me call this angle as theta 1, this angle to be theta 2. Now, as far as the phase response goes, you start off at this point as usual and go around the unit circle. When you are here at omega equal to 0, then both theta 1 and theta 2 make an angle of 0, and hence their difference also is 0. Therefore, the phase response starts off with a value of 0 here. And now, when you are at this point at omega equal to pi, then both vectors subtend an angle of pi. Therefore, the difference is again 0, and hence at omega equal to pi the phase response is 0. When you increase the frequency from omega to 0, when you go up around the unit circle, clearly theta 1 increases more rapidly than theta 2. Therefore, theta 1 minus theta 2 will be positive, and hence you can expect the phase response to increase, and then it will reach a maximum and then become 0 again, because we have fixed, we know that these 2 points the phase response has to be 0. The phase response is increasing when you are near the origin, and then eventually it will reach a maximum and then come back to 0. And because theta is 0, this is a 0 on the real axis, which means the system's impulse response is real. For such systems, magnitude response is even and the phase response is odd. Therefore, the phase response you can complete using the odd symmetry property to be like this. So, this is the overall phase response. Now, to get a further feel for what is going on, suppose the 0 is now closer than before, that is, compared to the earlier radius, we have a larger radius now. again at omega equal to 0 and omega equal to pi, the phase response has to be 0. So, nothing changes, but what does change is the rate at which the angle is going to increase when you have the 0 closer to the unit circle will be larger, and hence in the second case theta 1 will rise more rapidly, and hence you can expect the phase response to be something like this. All right. So, this is the general field that we have geometrically speaking. Now, let us do this in MATLAB to get the exact phase response. So, I have H, which is the frequency response. Now, let me make R equal to 0.8. The frequency response is B comma A. B is 1 minus R e to the j theta. Theta is 0, therefore, this stays as it is, and the denominator is 1, and I am going to evaluate this at 2000 points, and I am going to evaluate it around the entire unit circle. All right. Now, phase response 1 is the angle of the frequency response. So, this is, remember, frequency response is complex. I am using MATLAB's angle command to get the phase. Now, instead of let me just plot this. So, now it is the more familiar picture which I had drawn by hand. So, at omega equal to 0, or rather f equal to 0, you have the phase response to be 0, and at omega equal to pi, which corresponds to f equal to half, again you have phase response to be 0, and it increases, reaches a maximum and then falls off, and this is for 0.8. Let us now make this to be 0.9. So, this is okay, and then pH2 is angle H1, and then I have to plot pH2. So, now you see between 0.8 and 0.9, the rapidity of the increase in the phase near the origin has increased. All right. So, this is what we were expecting based on our intuitive explanation, and MATLAB indeed confirms that this is true. So, let us carry this analysis a little more. Now, what I am trying to show here is an expanded version around omega to 0, only that now my 0 is extremely close. So, when I am here on the unit circle, I am at omega equal to 0 minus. When I am here on the unit circle, I am at omega equal to 0 plus, and R is very, very close to 1, and this is an expanded view. And you can see that at 0 minus, this is the angle subtended by this 0. At 0 plus, this is the angle. And when I go from 0 minus to 0 plus, the change is nearly pi. And in the limit, when the 0 is on the unit circle, at 0 minus, the vector will be a tangent at this point, and 0 plus, the vector will be pointing like this, and the change will be exactly pi. Therefore, when the 0 is on the unit circle, the change when you cross the 0 will be pi radians. Now, algebraically what's happening is this: the phase response after all is tan inverse R sin omega minus theta by 1 minus R cos omega minus theta. Theta is 0, R is 1. Therefore, this is really sin omega by 1 minus cos omega, and then this turns out to be tan inverse tan pi by 2 minus omega by 2. This you can verify, and this turns out to be therefore pi by 2 minus omega by 2. And if you plot the frequency response at omega equal to 0 plus, the value of the angle is pi by 2. When omega equal to pi, the value is 0, and in between the variation is precisely linear. And this being an odd symmetric function, this overall phase response between minus pi and pi is this. So, you have pi by 2 minus pi by 2. Okay. And from this, the inferences you can draw are: when the 0 is on the unit circle, you see a phase jump of pi. Remember, this difference is precisely pi. So, this is one inference you can draw, and the location of the jump corresponds to the location of the 0. In this particular case, the 0 is at omega to 0, because all that will happen is when theta changes, this curve will shift to the left or to the right, that is all. And in this case, this happens to be centered at omega to 0, because that is where the 0 location is. So, the jump will occur exactly at the location of the 0, and the slope of the curve happens to be minus half. Therefore, the points to be noted are jump of pi occurs at omega equal to 0, and it happens at omega equal to 0 because that happens to be the location of the 0. And slope of the curve is minus half, and the shape is linear. All right. So, these are the inferences you can draw from the phase response, and if I now make R equals 1, now let me add this. Now, you see exactly what was discussed is now being verified numerically. So, the last curve added is case when R equals 1. So, the jump occurs at omega equal to 0 or f equal to 0. The shape is precisely linear, and you see this is roughly 1.5 something, and this is minus 1.5. This is in fact is in radians. Therefore, this jump is precisely numerically 3.14, which is pi. So, the jump occurs at omega equal to 0. The value of the jump is pi, but the shape is precisely linear, and the slope is minus half. So, these are the inferences that you can draw when you have a 0 on the unit circle. Moment you have this, you can immediately guess that any 0 on the unit circle will give rise to this kind of sawtooth waveform. And if the 0 location changes, 0 has to be on the unit circle for this shape to be present, and depending upon the angle, the curve will shift either to the left or to the right. So, any 0 on the unit circle will give rise to such a sawtooth waveform, and depending on the location of the 0, the jump will be happening at that particular location. Therefore, if I have a 0 here and a 0 here, and for simplicity, for illustrative purposes, if I make this pi by 4 and this to be minus pi by 4, then you can see that this 0, I will have a jump at pi by 4. Similarly, for this 0, I will have something like this, and the overall response will be something like this. This is the overall response. Again, the point to note is, when you are here on the unit circle, this 0 will contribute one angle, this 0 also will contribute another angle, but these two angles will be equal and opposite in sign. Therefore, at omega equal to 0, the phase response will be 0. Similarly, at when omega equal to pi, again both the zeros will contribute equal and opposite angles, and omega equal to pi, the phase response will go to 0. And now you are adding two sawtooth waveforms, each having slope minus half. Therefore, if you add two linear curves, each with slope minus half, the overall slope will be minus 1. Therefore, in this case, the slope of the linear region will be minus 1, because they are the result of adding two curves, each with slope minus half, and the jumps will happen at plus pi by 4 and minus pi by 4. And given the symmetry of the location of the zeros, at omega equal to 0 and at omega equal to pi, overall phase response will be 0. And in between you will have linear response except at the location of the jumps. And in this case, the system's impulse response is real valued because you have two complex conjugate zeros, and hence the phase response is odd symmetric. In general, you can have any collection of zeros on the unit circle, exactly the same behavior will be manifested. Therefore, if you have n zeros on the unit circle, then overall shape will be linear, because they are a result of adding sawtooth waveforms that we saw earlier. And jumps will occur at the location of the zeros, and the jump value will always be pi, and the slope of the linear region, remember you are adding n such sawtooth type waveforms, each sawtooth waveform has a slope of minus half. If you add n such linear curves, the overall slope will be minus n by 2. Therefore, any collection of zeros on the unit circle will rise to linear phase response except at the location of jumps, and the jumps will always have a value of pi, and the slope, overall slope will be minus n by 2. And if the collection of zeros happens to have complex conjugate property, then the overall phase response will be odd symmetric. On the other hand, if there is no such relationship between the zeros, you cannot expect the phase response to be odd symmetric. Phase response will be odd symmetric only if the impulse response is real valued, and that depends on the location of the zeros. If every zero has a complex conjugate pair, overall phase response will be odd symmetric, otherwise it will not be.